In general, calculating the inverse of a matrix is a long and boring thing. Even for computers, if the matrix is big, like a 10 by 10, 20 by 20, 100 by 100, it becomes very, very difficult, yes? Fortunately, there are some matrices for which calculating the inverse is really simple. So let's see those examples. So this is the case of unitary matrices. Do you remember what unitary matrices were? We could also call them orthogonal matrices when they are purely real. Yeah, but do you remember what they were? So let me refresh your mind. So a matrix A is unitary if and only if A's columns are an orthonormal set and this also was if and only if A times A dagger equals the identity matrix. You remember we showed this and I actually proved it in a separate video. Yeah? But now look at this final equation here. It should ring a bell because it's very similar to the definition of an inverse. So a matrix times some other matrix equals the identity matrix. So this means that when A is unitary, and let me do it. This means that the inverse of A is A dagger, the Hermitian conjugate of A. And calculating A dagger was very easy. Remember, you just had to do the transpose and then do the complex conjugate. Yeah. So this is how to calculate the inverse for a unitary matrix. Let's do an example. Calculate the inverse of this matrix. So this is a complex matrix. In general, it would be very difficult. We would have to start calculating minors and so on. It would be messy. But if we are smart, we can notice that the columns of this matrix are an orthonormal set. Let's check that. So the columns of this matrix are, the first column is 1 over square root of 2, 1, I, 0. The second column is 1 over square root of 2, 1 minus I, 0. And the third column is equal to 0, 0, square root of 2. So let's do the inner products between these vectors. So the inner product of C1 with C2 is equal to, you can test it and you will get 0. We did an example about this in the chapter 1 in studying inner products. The inner product between C1 and C3, that's even easier to check that it will be 0 because they don't have any element where the other is not 0. And the inner product between C2 and C3 is also equal to 0. So all the three pairs give us a 0 inner product, meaning that they are orthogonal to each other. But even more, the inner product of C1 with itself is equal to 1. You can check this. The inner product of C2 with itself is equal to 1, and the inner product of C3 with itself is also equal to 1. So this means that the inner product of Ci with Cj is the Kronecker delta of Ij. So if I is equal to j, this is equal to 1, and if I is different to j, the Kronecker delta equals 0. So this is the definition of orthonormality. So the columns are orthonormal. And this means that this matrix is a unitary matrix. So columns are orthonormal means that A is a unitary matrix, and this means that the inverse of A is the A dagger, Hermitian conjugate of A, which is A complex conjugate transpose. So let's do that. So a to the minus 1 is a complex conjugate transpose. So we have to do, let's first calculate the complex conjugate. So it's going to be 1 over square root of 2. So remember, the original matrix is here, 1, 1, 0, I minus I 0. So we do the complex conjugate. By changing the sign of the imaginary parts. So therefore, the inverse is going to be the transpose of this matrix. So to do the transpose, you convert the first column becomes the first row. The second column becomes the second row. And the third column becomes the third row. And this is the inverse of this. Oh, sorry. Here I should have written square root of 2. Because there is a square root of 2 outside. Yeah. So this is the inverse for this unitary matrix. You see how easy it was to calculate. Thank you very much.